Sorry about that. Um, okay. So again, yeah. So starting materials is actually not just anything you can possibly think of that would come together. You actually would need to specifically look up these starting materials and see if you can buy them or purchase them or get them in some way that at reasonable cost that you're willing to spend. That doesn't mean just money; it means time as well. Um, if it takes you 3 weeks to work up 1 gram of starting materials and you need to do that for 100 grams, that's not going to work, which I've also seen before. It's pretty funny. Okay, so this is an example of a retrosynthetic analysis. How can we synthesize 1-methoxy pent 2-ene, excuse me, from precursors containing 3 or more carbon atoms, or 3 or fewer, excuse me, carbon atoms. By the way, this is a very, very, very common retrosynthetic condition that everything needs to be 3 or fewer carbon atoms. Part of this is because finding things with 3 or fewer carbon atoms very rarely are those unobtainable. They're usually very obtainable. It's a little bit complicated now because of the large number of things that have been put on class 1, class 2 due to the fact that they can be used to make different illegal drugs. But anyways, typically 3 or fewer carbon atoms means it's obtainable. It's a very, very common condition in books especially. So if you're going to be doing this as practice in any sort of book, this is usually the condition. It's either 3 or fewer or 4 or fewer carbon atoms. And so we go ahead and overall we want to make this right here. This is our target that we're going to end at. And then we're going to have some sort of series of steps that are going to involve things that have 3 or fewer carbon atoms in them. These could have oxygens on those carbon atoms, etc., chlorides, whatever. But we need 3 or fewer carbon atoms, small chains. Okay. And so these are going to be what reactions we have learned that can form these new carbon-carbon bonds here. Notice that if we look at this is 1, 2, 3 here. This is 1, 2, 3 here. So we actually already have fairly small chains that we could assemble into this already. And so now we just got to go, how can we make these bonds? And that's where we're at right now. So we're going to look for places where we could make those connections. We've just went off of some triple bond stuff that you could attach new carbons at the end of triple bonds, right? And so we could break apart the different sides of these triple bonds, and that could actually get us what we want. So in this case, we're going to go ahead and choose this side, just a little bit less complex. So how would we use this chosen reaction? We have the retrosynthesis transform, which is going to be our target here, and then we're going to undo an alkylation, that alkylation we'd seen at the beginning of the chapter. And this is going to be a bromoethane on this side, and over here we're going to have a 4-carbon. Whoops, that's a bit more than we wanted, wasn't it? And so notice this would give us our final product, but this one right here is more than the 3 carbons we had wanted. So that is actually a problem there. That can't be one of our starting materials for this. Now we could do another transform or retrosynthesis and then make this one right here. But there is another option that would have been more elegant. And that is we could have had this one broken over here. That would have been another option, though that is complicated because it's next to an oxygen over here. So let's go ahead and do one where we're going to assemble this so we can get a 3 carbon or less. Again, we're at 4 carbons right now. So if we look over here, we've done a lot of methoxy work, haven't we? Where we've went ahead and done substitutions with a methoxy. Or you could say this is an ether synthesis. We just went through a whole chapter where we had like a significant portion of it dedicated to Williamson ether synthesis. And so this is a reaction, and we do a transform again. This is that previous precursor right here. This is then going to undo a Williamson ether synthesis, because Williamson ether synthesis would have been going this way, the opposite way, for our transform. And so we're going to get a bromo over here. That's going to be that target for this NaOCH3. This only contains 1 carbon atom. This one has 3 carbon atoms. This is going to be that SN2 Williamson ether synthesis that's going to attack that. And this would be our complete synthetic pathway in the forward direction. And so again, we start from the end here. We write that out. And so that is our reactant right there. That is the other reactant that we're going to put with that over here. And then we take our next step, and so we have this one right here. It's going to react, it needs a base, the hydride, to deprotonate that. And then it needs that alkyl group that we're going to be attacking right there. And that gives our final product. Now, there was an alternate retrosynthesis, and this is actually the one I probably would have went after first, but I guess I ended with it because I like it better. And so this one right here is breaking the bond on this side, because this is 1, 2, 3 carbons. This would then be the 4th carbon right there. So we will undo an alkylation right over here. And this is going to give us these two as our products. So here we have the bromomethoxymethane, and here we have the but1-ene, which is this side right here. Now notice again, this is too many carbons, and so we can actually do undo an alkylation again. I like this symmetry. I don't know what it is. If you let me do the same reaction twice, I always pick that one. It's something about me. Okay, anyways, so we're doing that same alkylation reaction twice here. Again, we have the bromoethane right here, and then we have the nice ethine, which, again, I very much like that, where you can use very cheap, easy gases. They're widely available to do your reaction. The only problem is here I end up using a bunch of hydride, which is a bit of an issue. But so we go ahead and do the retrosynthesis right there. We're done. We're down to small little fragments that can make this. And so we go ahead and take it and rewrite it. So that is the forward synthesis. And so we write this over here. And then we put the reaction conditions. And so that's a hydride to deprotonate that. And then we attack that group right there. That gives us that product. We then take another amount of hydride here. Technically, I guess you could probably just put it with the hydride. But you would get... So you would want to use equivalents of hydride here. 1 equivalent of hydride, so it doesn't attack over and over and over on the same spots. That could be a problem, getting side products here. Other different products you'd have to purify out, because this could actually react with the hydride and then attack another one of these, so you'd want to be careful. And so we go ahead and purify that. We get our hydride again, put it in there, and then we deprotonate that, and it attacks that group right there, and that gives us our final product. Okay, so let's propose a way to carry out the synthesis shown right here. And so here we want to go from an OH, we want to get a nitrile group on there. And how would we go about this synthesis? And so the typically kind of easier way is to go ahead and we'll go ahead and pause, try it out real quick, and then I'm going to move on to the actual solving it. Okay, so we need to somehow get rid of, if we're going to, usually we are going to want to go ahead and write this out as a retrosynthesis first, so that we can find the different reactions that we could possibly use to do this. It's going to be easier to find that. And so we want to go ahead and write out that we're going to break this nitrile bond right here, get rid of that, and we're going to want to somehow get this into something, an alcohol eventually. But for now, we just need to break this and undo that. So we can undo an SN2 reaction. This is a reaction we know, and a fairly easy to understand reaction for us. And what we could use here is we could use a bromo or iodo with a sodium cyanide or sodium nitrile. And that's a reaction we've seen a few times before. And again, this is going to be the first transform. All right, so this doesn't get us back to our actual reactant over here that we had said we were going to start with. So we need to go ahead and put in one more transform. And that transform is going to be going from the bromo here to the alcohol. Notice that this is actually that PBr3 bromination is a very elegant way of doing this that we have discussed before. And so that would be a good fit for this. Because remember, the phosphorus actually attaches to that oxygen, then bromo comes on here. So it's very tightly regimented. So we go ahead and put that. We take our retrosynthesis, we write it in reverse with the arrows and reaction conditions. And so we go ahead and take the alcohol, which is our original reactant, put PBr3 with it for the first step of the synthetic pathway. And that gives us the bromo. We then put the sodium cyanide with that, and that's going to give us the nitrile. Note in these reactions, it's very likely you're going to have to quench or purify these products before you go on to the next steps. Keep that in mind. In a synthetic pathway, it's not every single step that you could possibly need to do in it. It's just the reactions that you're going to be looking at with a little bit of indication. This right here is going to be some of the carbon nucleophiles and the opening of epoxides again. So this is an epoxide or an oxirane. And so here we have that alkoxide, in this case methoxide, and we'll have it in solvent, which is the methanol, and that's going to give us this methyl oxide, methoxy ethanol right here, just like we had seen before. And so this is another example of adding a carbon bond to this. We can add a nitrile to this. So again, we take the nitrile here, the sodium nitrile, and that's going to attack, open this ring, and then we work it up with water, which is that acid workup we had talked about in the previous chapter. So let's go ahead and talk about some of the other mechanisms for opening up these epoxides. We can use an alkanide anion. So the first step, we need to generate an alkanide anion, and that's with a very, very powerful base. In this case, again, sodium hydride, which is the most common one we use because it generates H2 gas. And then we go ahead and put our epoxide in once we have that alkanide. It's important that you do it in this order because this right here could react with this as well. So then that's going to attack the epoxide. That's going to cause the ring opening with the alkoxide coming over here. And then we got to do our acid workup. And this is the acid workup here so that we protonate and give us the alcohol. Notice again, we have made a new carbon-carbon bond. This is another possible way to make a carbon-carbon bond. And then we have this triple bond that we can add all sorts of things to it if we want. This is that mechanism again. I'm not going to really go over the mechanism here because I think I've done this like 3 times now. But if you ever want me to go more over a mechanism, I can. Let me know. Okay, so this is another one that will give us a new carbon-carbon bond. Here we have a lithium in ether, and so we have a ethyl lithium or a Grignard reagent will also work. Alkyl lithiums will work. Anything that gives a negative charge on that carbon will work nicely, actually. And so this negatively charged carbon is going to again attack one of the carbons in this ring. That's going to open that bond up. And then we need to do an acid workup again, and that gives us the alcohol and finishes the reaction. This one right here is the Grignard reagent in this case, and so this is kind of interesting because we're actually adding a benzene to it. So we go ahead and have the Grignard reagent. There's a negative charge right there. We're going to then attack that carbon again, and then that'll break that bond, leaving the alkoxide, and we'll have the acid workup again, which will go ahead and give us the alcohol. notice again we've made a new carbon-carbon bond. And so these are using those epoxides to form those new carbon-carbon bonds. We have rewritten all of these into retrosyntheses, and so these would be our precursors. In the case of retrosyntheses and precursors, we typically write them without the exact ions that would cause them to be like that. And so, for example, we could use sodium nitrile, but there's also other ones we could have used here. We could have used like a potassium nitrile, metal that leaves easily with the nitrile. And so there's quite a few metals that would actually have worked here to go along with that. Same sort of things over here. We could use various different powerful bases. All we really care about is we get this negatively charged right off of that triple bond. And so we just write those as the reactive species that we actually want. And then there's a variety of different products, things we could buy to get those reactive species, or ways we could set those reactive species up. All right. And so these are all those retrosynthesis indicating where we've made our new bond right there. All right, so let's show how to synthesize the molecule below, beginning with compounds that contain 4 or fewer carbon atoms. This is that other condition I mentioned, very common, 4 or fewer carbon atoms. Really, it's just a thought experiment. In reality, what you would actually want to do if you're doing this in industry is you would want to go for things that you can easily find on something like Sigma Aldrich, where you could order these chemicals, and they are not ridiculously priced. And then you'd want to work up things that eventually would be cheap and plentiful and easy, and you can source well. That may not be Sigma Aldrich, by the way. There are much cheaper chemical manufacturers than Sigma Aldrich or Flynn, which is what the educationals, we as a university would use. But you gotta order those in like dump trucks, which we don't use in that much. Okay, so go ahead and pause here and go ahead and try to work on this, and I'm gonna go on to the next. So what we're gonna do here is we're gonna look at this and we're gonna trace out. Okay, so we want 4 or fewer carbons. If we go this way, then we're going to have a 1, 2, 3 fragments minimum. If we go this way, we're going to have 1, and this 1, 2, 3, 4 over here. And so we could do this in 2 fragments. So the first thing we need to do is we need to figure out the first bond arrangement that we can apply to the transformation. Okay, so we could go on this side, or we could go on this side. Those would both work. And so we could use an oxirane, epoxide ring opening, transform, and these would be our 2 options. I personally would prefer this one. I think it is more elegant. This would require more steps. Every step is losing product. And so this would be the one I would prefer, is going on this side. And so I go ahead and set up this oxirane right here. And again, that's 1, 2, 3, 4 carbons. And this one right here is going to be my attacking species. I could use a Grignard reagent. I could use a lithium. There's a few different varieties I could use. I'm going to go ahead and do this as a Grignard, actually. And again, this is the epoxide. This is it written. So we only needed this one transform because we chose this side to break it. And we're going to go ahead and rewrite this as a synthetic forward step. And so we flip around those reactants and product, and we go ahead and go over here. Again, that's the epoxide. This is going to be the Grignard reagent put in first. And then we need an acid workup to finish that to the alcohol, actually. Without the acid workup, we would have had O- here. All right, so let's go ahead and talk a bit about the alkylation of alpha carbons and the regioselectivity and kinetics versus thermodynamics control. So if we put these 2 things together, we have our aldehyde here, or a ketone in this case, and this is going to be treated with alkyl halide alone. And what we would end up saying is we would have no reaction. This would not actually give us our product, despite the fact that we would normally think of these as something that could perhaps attack. So we actually require a base for the alkylation of an alpha carbon. And so what we need here is a bit of base. In this case, we're going to use that sodium hydride in THF. And then we're going to treat it with a methyl iodide. And so what's going to happen here is we're going to go ahead and take off. We're going to go ahead and get the substitution happening right here. Notice that this is the carbon in the carbonyl. This one is the alpha carbon. That's why this is the alkylation of the alpha carbons. This one again, this is the carbonyl. This one here is then the alpha carbon. And so we get the alkylation of the alpha carbon again here. Again, note that these are both going to generate new carbon-carbon bonds, and we're using these strong bases to do this. So you may have noticed that this is going to be the alpha carbon, which typically has the acidic proton in these cases that we would have done like an elimination with, right? But because we're next to a double bond carbonyl, we're going to stabilize that negative charge. And so the first thing is we use that strong base. It has to be a very powerful base, something like hydride, or that amide base that we had looked at before. This one right here, the sodium amide. So the first step is going to be the proton transfer. This is going to be the base attacking the alpha proton. Remember, that's the alpha carbon right there. And that's going to leave a negative charge on that. Now, that's usually extremely reactive. And what would end up happening is you'd pull something over, leaving group would leave, and we would end up with a double bond, right? And so that kind of does happen. So you could think of it as, this is the enolate ion when you do that. So if you were to go ahead and pull these electrons over into a double bond, the electrons on this oxygen would actually come up here, and that's going to give you this product here, right? And the leaving group doesn't actually leave because it has a double bond. And this generates our enolate anion, actually, which is, again, it has the negative charge on both this oxygen and this carbon, and that negative charge is being shared. And so that helps to stabilize this, so we can actually have some time to have another reactant group come in. In this case, we're going to have our bromo-alkyl group right here, and this is going to attack, because it has a negative charge here, that carbon right here, and bromo is going to leave as a leaving group in a nice SN2 reaction. And so we have now added a new alkyl group on that alpha carbon, which is quite nice. Again, we're building up our tools. The alkylation on alpha carbon is going to be straightforward if there's only one distinct type of alpha carbon to consider. In this case right here, we only have one alpha carbon. In this case here, both of these alpha carbons are the exact same. There's no difference. And so it doesn't matter which one it actually attacks. The regioselectivity is going to be a concern for the alkylation of ketones that will have distinct alpha carbons. So in this case, we have this one here, and then we have another alpha carbon that's different. And so this would be the alpha carbon right here, having the alkylation occur, and that will give us this product. The alkylation occurs over here, that's going to give us this product. So how can we distinguish between these two regions so that we can try to target one versus the other? Well, you may have noticed that many times when we're trying to distinguish between two areas that have a substitution and are less substituted, one of the best ways to do that is just make our attacking group, the thing that's going to have to get in there and attack, bigger. If we make it really bulky, then it's going to do a faster reaction where it's more exposed and a slower reaction where it's less exposed, right? And so we can go ahead and do that actually. We can choose a base depending on its bulkiness. And so right here, this is the LDA. It's a very bulky base. You can see it's a lot of CH carbons off of here, making it very large. We put that with excess THF and pentane at negative 78 degrees Celsius. Notice we need to actually slow this down still so we can get some difference. And so that's going to give us the alkylation faster at the less substituted side. That'll give us 52% for this product, which is the less substituted side. If we go ahead and use something that's a little bit of a less bulky in terms of our base, we can go ahead and get this at a little bit higher temperature, 50 degrees Celsius, quite a bit higher temperature actually. This one's going to go ahead and alkylate at the more substituted side. It's 41%. Okay, let's go ahead and look at the mechanism for these. Oh, man. Okay, so this is the one that's going to happen at the more substituted side. And so here we have the LDA, that's its basic form, and this is going to attack the hydrogen on the less substituted side preferentially. This is then going to give us our enolate ion right here. That's that resonance structure. And then we're going to go ahead and attack on the carbon right here, and that's going to be our SN2 reaction where the bromo leaves. And that gives us our final product. So if we look at the other one, notice again we have greatly bulked up the exact place where the base is, right on there. We go ahead and look at the other one, and so again we have this base right here. This is going to attack the less substituted side, and this is going to give us our proton transfer step again where we have the negative charge there, and that's going to give us our SN2 reaction again. And so again, very similar mechanisms, the big difference being what we're using as a base here and which side ends up being attacked preferentially. And so let's go ahead and look at that step in terms of energetics. Okay, so we can go ahead and understand why one side gets attacked faster than the other. So for the LDA here, we're going to attack the less alkylated side. This deprotonation is going to end up being irreversible, and products are going to be heavily favored. So this is going to be where we have a fairly low barrier to overcome, and then we go over to the products, and the products are thermodynamically very favored here. And so going backwards with that same amount of energy that's available to us becomes essentially impossible. So we only have this amount of energy available to us, right? And we just need to get somewhere here. If we use that same amount of energy, we're not even close to coming back. And so it becomes an irreversible reaction, actually, under these conditions. This one right here, the deprotonation, on the other hand, for this one, with the alkoxide base, that's that second set of reactions that we did, this one's going to actually be reversible. And so the energy barrier's low, and in fact, our products are actually higher energy, just by a bit, than our reactants. And so we can go back and forth on this reaction. This will actually create an equilibrium, in which case we actually end up a little bit favored on this side, which is why our product is not a huge percent yield, 41%. That's part of the reason for that. And so when we have this one, this is going to be kinetically controlled. It's going to be which one would react faster versus which one reacts slower. This one's actually thermodynamically controlled, which one is more stable, because we actually are going to get stuck here. This one right here is going to end up going to the product period. And this reaction becomes irreversible, so whichever one happens faster, it's going to get stuck in. This one is going to reach equilibrium. If we leave it sitting there, the reaction speed is going to end up not mattering at all. And so what will end up happening, I actually reversed that completely, is going to be that you're going to end up with the thermodynamically favored product. So for products from competing reactions to be in equilibrium, there must be a way the products can be interconverted one to another. And typically this is not going to be directly. This will be back through the reactants, though you can happen directly. It's very unusual. So here we have reversible reactions. When we have reversible reactions, these are going to keep going back and forth over and over and over as we wait in this reaction at equilibrium. And so we can go ahead and write these as a direct equilibrium, because this middle step doesn't really matter to us much. We don't really care if we end up with the reactants sitting there. And so our products end up in equilibrium. And then because they're at equilibrium, we're going to end up with present in the products of greatest abundance. Regardless of how fast it is, we're just going to end up with what's thermodynamically favored. And this is how you achieve a thermodynamic control with speed not being a real factor, because it's going to just continuously invert back and forth. And if you remember your equilibriums, the amount that you end up with on each side is directly controlled by the thermodynamics of how stable each of those sides are. Same as the acid-base reactions and all the other equilibriums did in Gen Chem 2. If the competing reactions are irreversible, however, you end up being heavily reliant on the speed. It doesn't have time to go back and forth. It doesn't have the ability to go back and forth. So it can't rebalance. And so whichever one's faster, you end up just building that up. The slower one doesn't build up as fast, and you can't invert back and forth. And so irreversible reactions go from reactants to products. There is no reversal, and so you can never form any equilibriums at all. There's no backwards in the reaction. So reversible reactions are going to always end up with thermodynamic control, because you can always go back and forth in them unless you've done something to very, very quickly stop and quench the reaction before it can achieve equilibrium. There are possibilities to mess with this a little bit, but overall, this is a great rule. Reversible reactions are going to form equilibriums. Equilibriums are always thermodynamically controlled. Irreversible reactions are going to tend to be placed under kinetic control, because they don't have time to balance back the equilibrium, i.e. they don't have time to achieve a thermodynamic equilibrium, thermodynamic populations of the states. What they end up is just trapped wherever they happen to end up. All right, so we look at this, and this is actually a case where we have kinetic and thermodynamic enolate anion. That's why with the two different bases actually caused us to have a difference in the amount of product we got for each of these, to have one have a different product that's favored over the other. And so this one has less steric hindrance, and this is a faster reaction than this one. This one right here is a slower reaction because it's harder to get in there. So when we used a big bulky base, we ended up having this have a lot more steric hindrance over here, less steric hindrance over here. And then we used a base in that case that the energy differences were large enough that you end up with an irreversible reaction. And so we had a kinetic enolate anion and a kinetically controlled product. The other way, where we had the alkoxide, that one was a reversible reaction. And so we could go ahead and go back and forth, back and forth, back and forth. And so we get the thermodynamically favored enolate anion. This right here is actually more stable because it's a trialkyl substituted double bond, which, if you remember from our previous chapters, the more substituted a double bond is, the more stable it is. All right, so this is going to be using these in various different senses. The alpha carbon would have an additional hydrogen in the ketone or aldehyde. This alkyl group would come from the alkyl halide right here. And so when we undo the alkylation, we get this right here, which has one less substitution. And so we can go ahead and use this to put on various new groups here at these different spots. And depending on which one we use, whether we use a oxide right there or the LDA here, we can again get a product that's going to be favored based on thermodynamics or based on kinetics. And so we can actually choose which of those we would get in the higher amounts, which is quite nice. It gives us an extra tool in our toolbox here. Now, there are traps in synthetics, syntheses that you have to be quite careful of. When we apply a transform that undoes a particular reaction, we tend to focus just on those specific changes that we want to occur. This restricts our thinking in a way, and so we can encounter what would be referred to as a synthetic trap. In fact, where we have factors that we have narrowed our vision so much that we no longer are seeing. So here we have a target here that we want to achieve, and we have to synthesize this from starting materials containing 3 or less carbon atoms. Okay, we have this in our mentality. We're doing this. And so we can actually apply, we can run into a bit of a trap here. This is going to end up with a trap. And that is right here. These were the materials, and we went, okay, we have epoxide, we have this substituent right here. I think we can go on to here. Okay, fantastic. We're doing great. And then we go ahead and run the reaction, and what we would end up getting is to attack the other carbon. We would not actually get the product that we thought we were supposed to get. So notice again, it would attack the less hindered carbon because this is again an SN2. This is going to be the favored attack. And that's going to give us the wrong product. And so we would actually try to do this reaction and we would get completely the wrong product, and we'd sit there going, what the hell are we going to do now? However, there is another way we could have done this. And so what we could have done is we could have used a strong base, which is the Grignard reagent, with a strong acid here. And if we did that, then we would actually get this product, which again is not the product that we were trying to get. And so we've pitted ourselves into a bit of a trap here. And this is not going to lead to our intended product, which is that one right there, because we have put right here the retrosynthetic undo epoxide ring opening, and we've now stuck ourselves in this problem. However, we can go ahead and roll back our retrosynthesis and go, okay, the epoxide's not working for me. What else do I know? What could possibly do this? And so there was another reaction we know of. It's the undo alkylation. Okay. And so you could do an undo alkylation, in which case we would use the triple bond here. And we would add that over here with a bromo right there. Oh, I'm sorry. I didn't actually put in how to solve this. So there's actually a few different ways we can solve this here. We could break this up into 2 steps. That would also work. In which case we have like a leaving group here and a strong base, and we just attack this over and over. We could also put a triple bond and hydrogenate this. There's a few different ways. Again, when we're looking at retrosyntheses, there's actually, it's like any other toolkit and we're trying to build anything. There's many pathways to the end. I'm just going to show you some traps, I guess. I guess I didn't. It seems like I kind of forgot to put in any how you solve it. But the big way to solve it is usually to go, if my retrosynthesis step that I had listed is not working out for me, step back, and sometimes you need to like take a break, go get a meal or something. And then what you need to do is scrap that retrosynthesis step and try something different. Okay? And then think about like what could give you a different product. Focus on that. Sometimes you even have to roll back a couple retrosynthesis synthetic steps. So again, these are very likely to occur when there are 2 or more functional groups on a precursor that can react in a particular synthetic step. This is probably your biggest problem, actually. if I had to list the thing that causes the most frustration, and we haven't talked about protecting groups yet, which is part of what would cause the issue here, is many of the functional groups you may have noticed have very similar reaction conditions. If you look on those tables of the reactions that we've covered. And so you can get reactions on various different groups. For example, a hydrogenation is not going to just get rid of a double bond that you want to get rid of. It'll also get rid of the triple bond, double bond, all the other triple bonds and double bonds, even the ones you don't want to get rid of. And so it's very easy to end up just getting rid of a bunch of functional groups and having all sorts of other reactions that you're not targeting. And so right here, we're doing a retrosynthetic undo the alkylation here. And so we have the propyne, and we have the 3-bromo, 1-propanol. Now, if we go ahead and put this strong base here, we'll get this negatively charge on here, and it's going to attack areas where the carbon has a bit of a positive charge to it. Now, what does that mean? Well, we got a problem. This right here, yes, that's the SN2 reaction, but this is an acidic proton, isn't it? And so this is an extremely powerful base, and it's going to go ahead and attack that. It'll actually generate the alkoxide ion, and you'll do a proton transfer. And so you never actually get the SN2 reaction. Instead, you get the alkoxide here, which could actually come back and react on self, could do a variety of different things. And so, yeah, we messed up. We got a problem. And we've put ourselves in a trap, right? Now, this, like any other art form or any other form of building things, it just requires practice. It's something that you're going to develop skills, and it's going to have to be something you just practice. You can create your own problems, in fact. A lot of people do that if they're learning this on a higher level. They would do these retrosynthesis. There's like a tradition for doing LSD retrosyntheses, and then figuring out like the optimal path to it, not looking it up. And then like that's a rite of passage because it's just a funny thing to do it for. So you can create your own problems. You start with a structure that's a relatively small number of carbon atoms, contains functional groups. You know you can participate in a reaction that we have studied. You can carry out reactions in the forward direction. You keep track of reagents and conditions and determine the product. Pay special attention to stereochemistry and regiochemistry. Stereochemistry and regiochemistry are, if you're going to mess up, it's probably where you're going to mess up. That and reacting away functional groups you weren't targeting. Repeat until you have created a product that is a result of 2 or 3 sequential reactions. Treat the final product as a target and ask how the target can be made from your starting structure. And so this is how you would go about designing problems for yourself. So here we have your own synthesis problem and examples of how you can do that. And so here we have this step right here that's going to give us our alcohol here from our ether. Here we have the alcohol going to the bromine. And over here we have the these two doing an alkylation. So let's go ahead and look at a synthesis then. So we have this right here as our starting, going to that, which is our final product. And so the overall synthesis we just did, but we now can phrase it as a problem. So now we're going, how would you do that synthesis? You would then swap that to a partner, somebody you want to challenge. This is actually can be pretty fun. So like one of the things that people are going through organic grad school have a tendency to do is they kind of play like a game of this, where like they design their problems and then swap them, and whoever can solve the other person's problem with the more elegant workout faster, that person gets a meal bought by the other person or a drink bought. It's just like low stakes things. I guess meals are pretty high stakes now. Probably a drink. Usually a beer or something like that. And so you swap problems, and the other person has to design a synthetic pathway from this to that. Usually you just stop at the retrosynthetic pathway, but you can go all the way. And so you then would see if your proposed syntheses have any synthetic traps in them. How can you overcome that trap and work around it? And it's interesting because again, that practice builds tools in you that you can use to then overcome those sort of traps, like common pathways, like a video game. So suppose your study partner constructed the following synthesis problem, gave it to you to solve. Let's design a synthesis that can be used to carry out the transformation. And so we go ahead and have this. Go ahead and pause it. Try to do that. I know I've provided enough problems that you probably don't need a partner to do it for you, but we're going to act like your partner did it, not me. Okay, and so what's a pathway we could go? Well, we want to start from the retrosynthesis, right? And so we have that double bond. We are going to want to undo a hydration. That's probably going to be our most, that seems like a pretty good way of getting that double bond in there, which would be the dehydration. So undo a dehydration, that would give us an alcohol here. Alcohols are fairly reactive groups that we can work with. The next step is then going to be taking this precursor and we're going to generate that. And so we're going to undo an epoxide ring opening because those always give us alcohols. And that's easy to go ahead and just add anything we want to the epoxides, right? And so we could go ahead and use a methyl lithium alkyl lithium, excuse me, and the epoxide right here. And again, that would be attacking over here to put the methyl on there. Okay. And then finally, we're going to undo an epoxide ring formation so we can get something a little easier to get our hands on. One of the things that's really good for undoing epoxide, forming an epoxide would be a halohydrin. That's one of the things we've covered so far. And so now we take our retrosynthesis, we write it in reverse, and we go ahead and put our reaction conditions. So here's our halohydrin. This needs to be in the presence of NaOH as base to go ahead and deprotonate that. And then we're going to get the epoxide. The epoxide then is going to be treated with the methyl lithium here. And that's going to have an acid workup to get us to our alcohol right here. We're then going to put a concentrated H3PO4 that's going with heat. That's going to give us our dehydration. An interesting little side note to this is we could have probably combined these acid workup steps into something so that we didn't have to do this so much. I think that actually would have been okay. And we probably want to purify before we do this, actually. I look at more. That'd be something you'd have to play around with experimentally. Yeah, I kind of wonder if you could. Anyways, if you do it in 2 steps, you can purify in between and make sure you don't get any side products. If you do it all in 1 step, you might have issues with some side products that you have to purify away later, which might be more difficult. So the green chemistry, this is a major thing that's we've been working towards for the last 40 years. And so a lot of the people don't realize that in chemistry, a lot of the time that used to go into forming new reactions and forming new things to test and testing new drugs, a lot of that is gone into what's called green chemistry. And so these are setting up guiding principles to help prevent various forms of pollution and other hazards. The goal is actually to avoid accumulation of hazardous materials in the first place. This can depend on development of green alternatives. These can involve things like new reactions, new techniques, new technology. The American Chemical Society has 12 principles of green chemistry. They're located right there. I'm not going to cover all of them, but essentially it is a combination of efficiency and trying not to use things that are particularly poisonous, like halogenated compounds are quite poisonous. So that's actually one of those areas that I've showed you a lot of halogenated compounds. They're easy to do reactions with, but they typically are very not green. And so, for example, the things where I was showing you acid, Catalyzed reactions with alcohols, those are much more green and much easier to handle waste for. So this is an example using less toxic reagents. It's a very important principle. And so BR2, this is toxic. It causes burnt skins. It damages the respiratory tract if inhaled. It's very dangerous to work around. It's dangerous to have in the environment. Overall, a much more hazardous pathway. We can instead use HBr with peroxide, hydrogen peroxide, and this gives us a same product, usually decent yield and just as good of yield in terms of money and time that we could work up with this, and far less hazardous. So everybody that's around is happier and we have less problems. Okay, so this is another example. This right here is quite reactive, of course, but being reactive is not necessarily in and of itself a completely hazardous thing. So once you get to a certain reactivity, you don't have any long-term effects because it just reacts with anything next to it, and so you have no long-term anything. It's just gone as soon as it comes into contact with the environment. However, things like DMF, on the other hand, a solvent here, this is readily absorbed through the skin and is a liver toxin. And so those DMFs you've been seeing as solvents in several of these different reactions, it's actually quite dangerous to work with, and it's dangerous for everybody around it. And like if you were to pour this out into just like down the sink, it could come in contact with people and cause liver toxicity. It's not a great solvent in terms of safety. And so you have two options here. You could use DMF or you could use water. Water is a hell of a lot safer. And so you could use water here and you would greatly decrease the amount of damage you would do to the environment and people around that are actually working on these factories or facilities. You can go safer. There's actually kind of a funny thing. Lithiums and so there are these facilities that do like silicons and lithiums, and they work with these highly explosive compounds, and they actually produce these facilities in long rows of little house things that they build, little labs, and then they have these the equipment so you can literally just plug it into the sides of these buildings. And the reason they do that is all of them are detached, and it's because they actually burn down the labs like every few months. And so, one of the major things in chemistry is some of this stuff is just incredibly explosive. And lights on fire just with the slightest contact of the atmosphere, boom, gone. And you got fire and you got to get the hell out of there. And so this is, again, diazo, and it's very explosive, very reactive, and typically the biggest problem makers are gases because they can escape fairly easily and blow up. Now, the product here is actually fantastic. Nitrogen gas is as untoxic and unharmful as you can get on this planet. This reaction is a lot safer, though. And so right here we can use methanol and sulfuric acid. Sulfuric acid is a lot less dangerous than an explosive gas. The product is water, and again, that's quite a safe product as well. So not much of a problem there. All right, and so one of the other things we can do is minimize byproducts and other wastes that we're going to have to purify and get rid of. That cuts a lot of steps of solvents you'd have to use and other things we have to add. I would like to point out that most of these things are, yes, they are green, and so they help the environment and the safety of people around you. But oftentimes making things more green also saves money. For example, you're going to have to pay the person that's exposed to toxic, harmful chemicals on a daily basis a lot more money to do that job. Exploding the lab costs money. These instruments and this equipment is expensive. And so for the most part, the incentives are actually aligned, which is quite nice. It really has helped. And this is why the green chemistry has been a big thing over the last 40 years and has made incredible progress. Though it is at the expense of some other research fields, which is always true. We research what we value. So we can minimize byproducts and other wastes. Again, by minimizing byproducts and other wastes, we can have less workup that needs to be done. For example, we have two reactions right here. This one creates the desired product and then has unusable products that we then have to get rid of. This costs money to get rid of. It costs time and money to get this product by itself and not have this crap next to it. However, if we have a reaction where everything gets used and there's no byproducts at all, then we don't have to do purification steps. We can just move forward, and we don't have to spend the extra time, money, equipment, everything else on that, which is quite nice. And so this is referred to as atom economy. It's where you use up all the atoms in the reactions and you don't have any extras that you have to deal with. Or you use up most of them and have less extras to deal with. Overall, it's a great trend towards a more green chemistry. And so atom economy is the mass of atoms in the desired product divided by the mass of atoms in all the reagents that you use times 100%. So let's compute here the percent atom economy of the eliminated reaction shown in that equation above. And so right here, we would take all these atoms right here, add them together in terms of mass from the periodic table. And then we take this side and we'd add all the atoms from this side up, and we would get our mass from the periodic table. There would have been a quiz, but I'm going to skip through that. Okay, and so we go ahead and add those up. And the molecular formula for dibromide and its mass is this right here. The mass for each formula unit of the NaOC-CH33 is 113.13 from the periodic table. So the mass for the two formula units together, if we add those together, two of these, notice we use two equivalents of these, is 226.26, and then we add that to this number here, and that gives us our 490.22 that was on our reactant atom side. And so the next thing we have to do here is we have to go ahead and look at our product, our desired product. How much of these atoms is used to make that desired product? So we take our desired product, add all that together, and that gives us 102.14. We put that in on as our numerator. We then divide it by 490.22. That would give us 0.2084. We want to get in percentage, so we times it by 100 to get percentage, and that's 20.84%. And so we have a pretty low atom economy there. We actually have a lot of our mass that ends up going down into waste. Now, having said that, atom economy is kind of like the elementary school stage of understanding these things. So for example, we could greatly improve our green and efficiency of this if we can recycle these and then use them for something else. Even though our atom economy might be pretty bad still, we would then recover those and use them for something else. But atom economy is a great first step to understanding how to make something more efficient, how to make it less waste that has to be dealt with. Remember, waste always has to be dealt with. If you make enough of anything, it'll be poisonous and problematic. Doesn't matter how benign it is. CO2 is probably one of the most benign chemicals you can make on the planet. Probably within the top 10 most benign chemicals you can make on the planet. And yet we're having a problem with overproducing CO2. And so you can literally have heat pollution, light pollution, water pollution, where you're producing too much water in an area. Yeah, if you produce enough of anything, it can be a problem. So to minimize the cost of synthesis and to help make the synthesis as green as possible, the percent yield of the target should be maximized. You can do two basic rules to help you maximize this percent yield. The number and the steps of the synthesis scheme should be minimized. Even if everything is a 90% yield on every single step, the more steps you do, the less it comes. Remember that every time you have a step, you would take those percent yields and you'd have to multiply them. So if you do that, 20 times, you may be 90% every time, but you're going to be down in the 50% after you're done with those 20 steps. It's going to be drop off really bad. Each step in your synthesis should proceed with the highest possible percent yield. You can increase those percent yields. This is a careful balance that usually has to be maintained. There's times that you're going to be able to increase percent yield by breaking into steps, and you'd have to multiply those steps and see if that gives you a better yield than just doing one step, even though it might only be an 80% yield or something. Or a 70% yield. It's a careful balance that has to be done. These rules are essentially an outcome of how percent yield is computed for a linear synthesis. The synthesis composed of sequential steps, and so you would have percent yield that would compound over the series of those sequential steps. So again, the linear synthesis, the overall percent yield is going to be equal to the product of the yields of the individual steps. You would take each percent yield, 90% let's say, and then 85%, and you would multiply those together, and that would give you your overall for those two steps. And then if you have a third step, you'd multiply that into those, and that would give you the overall for the three steps, and so on, and so on, and so on. And so here we see a bit of an example. We'll consider two syntheses, one with 3 synthetic steps and the other one with 6 synthetic steps. So both syntheses got 80% yield for each step. What would be the overall yield for these? So the 3 steps would be 0.8 to the third power, or 0.8 times 0.8 times 0.8, which is 0.51, 51%. If we did that in a 6-step yield and every time it was 80%, we would get 0.8 to the 6th power, and that would be 26%. And so the fewer steps greatly helps us out here. But keep in mind, again, it's a balancing act. So here we see that, for example, 5 steps at 90% yield gives us 59% yield overall. However, if we have 5 steps at 70% yield, that's only 17% yield. We could do 10 steps at 90% yield, and that would still give us a better overall yield. And so typically the number of steps does have the, if it's a large difference in number of steps, it usually is a pretty large difference. You can see even at 90% yields, 10 steps we're at 35% yield. We could do 5 steps at 80% yield and have almost the same. So if we got like an 83, 84% yield on these 5 steps, we're better than the 10 steps at 90% yield. So it's a careful balancing act. But overall, you would need to do that balance, because these, like this Taxol, for example, that we had looked at the very beginning of this, it consists of a 15 to 30 step synthesis, and the overall yield actually yields something that's about 5%. And so we actually end up using a massive amount of reactants to make that Taxol. But keep in mind that that 5% is actually a huge improvement over the beginning. So when they started that synthesis actually was a 2% yield. And so it was, they more than doubled it from very carefully trying to shrink the number of steps and get the highest yield they can in each step. So convergent synthesis, portions of a target molecule are synthesized separately, are then assembled together at a later stage. Essentially, it's where you take syntheses and they're branched and they come together later. The yield can be generally improved over a linear synthesis with the same overall number of steps, because remember that we're not going to compound every single percent yield then along the same one. So this is a linear synthesis up here with this number of steps here, and then we have the same number of steps down here, but this is a conversion synthesis where we do part of the structure and then we take the other part of the structure and then we combine those two parts of the structure. And so what you see here is that because of a conversion synthesis, we don't lose everything every single step. And so we don't compound every single step together. We're only compounding these steps together right here, then these steps together here. That then has one last compounding that happens to the overall thing, and then we get 41% yield. And again, you can do that fairly easily mathematically. These ones just directly multiply to each other, and that gives you 21% yield overall. These ones, you'd go 0.8 times 0.8 times 0.8. You'd get that number. You'd then take 0.8 times 0.8 times 0.8. You would get that number. And then those would be the base number. You would then times that base number by 0.8 again. And that gives you your overall yield. Right there. Okay. This is, by the way, just straight up like probability statistics sort of thing. It's just straight up the same probability numbers that you would do in like whenever you do percents. There's no difference in this. Like, this is just general basic math. Not special chemistry math. Okay. You have a wonderful time. I will see you next time.